Assalamualaikum and salam sejahtera. In this lecture, we are going to discuss about two types of asymptote, which are vertical asymptote and horizontal asymptote. Firstly, we look to the vertical asymptote. From the given graph, here, the vertical dotted line, which is at x equal to a, is called a vertical asymptote. The function f has a vertical asymptote at x equal to a because when x approaches the value of a, fx gets large or low without limit and never quite touching it. Now we look to the definition of vertical asymptote. A line x equal to a is a vertical asymptote of the graph of the function y is equal to fx if either limit fx when x approaches to a from left is equal to the infinity or negative infinity, or limit of fx when x approaches to a from right is equal to infinity or negative infinity. Now we look to the example 1. Find the vertical asymptote of fx equal to 1 over x squared. To find the vertical asymptote, we take x squared is equal to 0, so x is equal to 0. So we can say that the vertical asymptote is x equal to 0. Now we look to the example 2. Determine the vertical asymptote of a fx equal to x plus 3 over x plus 2. So the solution is for the fx equal to x plus 3 over x plus 2, to find the vertical asymptote, we take x plus 2 is equal to 0, so x is equal to negative 2. Since the limit of fx when x approaches to negative 2 from left is equal to negative infinity, and the limit of fx when x approaches to negative 2 from right is equal to infinity, hence x is equal to negative 2 is vertical asymptote of fx. Now we look to the example 2, part B. Determine the vertical asymptote of fx is equal to 1 over x squared minus 1. So we take the x squared minus 1 is equal to 0. So x minus 1 times x plus 1 is equal to 0. So x is equal to 1 or x equal to negative 1. Since limit of fx when x approaches to 1 from left is equal to negative infinity, and limit of fx when x approaches to 1 from right is equal to infinity, and also the limit of fx when x approaches to negative 1 from left is equal to infinity, and the limit of fx when x approaches to negative 1 from right is equal to negative infinity. Hence, x is equal to 1 and x is equal to negative 1 are the vertical asymptote. Now we look to the example to part C. Given that fx is equal to 2x over x squared minus x minus 2, by taking x squared minus x minus 2 is equal to 0, so we have x minus 2 times the x plus 1 is equal to 0. So we have x is equal to 2 and x is equal to negative 1 are the vertical asymptote, since the limit of fx when x approach to 2 from right is equal to positive infinity, and limit of fx when x approach to 2 from left is equal to negative infinity, and the limit of fx when x approach to negative 1 from right is equal to positive infinity, and the limit of fx when x approach to negative 1 from left is equal to negative infinity. Hence, x equal to 2 and x equal to negative 1 are the vertical asymptote. Now we look to the horizontal asymptote. A line y is equal to b is a horizontal asymptote of the graph of function y is equal to fx. If either limit of fx when x approach to infinity is equal to b, or the limit of fx when x approach to negative infinity is equal to b. For example, from the graph above, as x approach to infinity, gx approach but never reach the value of 0. By using the limit notation, we state that limit of gx when x approach to infinity is equal to 0. Hence, gx has a horizontal asymptote of y is equal to 0. Now we look to the example 3. From the graph above, we can see that if x approach to negative infinity, fx approach but never reach the value of 4. By using the limit notation, we state that limit of fx when x approach to negative infinity is equal to 4. And fx has a horizontal asymptote of y is equal to 4. We continue our discussion with the continuity, and we look first to the definition of continuity. A function y is equal to fx that can be graphed throughout its domain with one continuous motion of the pen, that is without lifting the pen, is an example of continuous function. From the graph above, we can see that for the figure 1 and the figure 2, it is continuous since they can be drawn without lifting your pencil. And for the figure 3 and figure 4 are not continuous because of the breaks in the function. Now we look to the definition of continuity at a point. A function y is equal to fx is continuous at point C if and only if it meets all three of the following conditions. Number 1, fc exists, it means f is defined at c. And the number 2, limit fx when x equals to c exists if and only if limit of fx when x equals to c from right is equal to the limit of fx when x equals to c from left. And the number 3, the limit of fx when x equals to c is equal to fc. Now we look to the continuity at a point A, B, and C. From the figure below, we can see that continuity at a point A is a continuity from the right, and continuity at a point B is continuity from the left, and the continuity at the point C is two-sided continuity. Continuity at n interior point. A function y is equal to fx is continuous at n interior point C of its domain if limit of fx when x equals to c is equal to fc. And for the continuity at n endpoint, a function y is equal to fx is continuous at a right endpoint A of its domain if limit fx when x equals to a from right is equal to fa. And a function y is equal to fx is continuous at the left endpoint B of its domain if limit fx when x equals to b from left is equal to fb. And for the discontinuity at a point, if a function f is not continuous at a point C, we say that f is discontinuous at C, and or C is a point of discontinuity of f. Now we look to the example 4. Discuss the continuity at the point 1, point 2, and the point 4. Limit of fx when x equals to 1 does not exist. Or we can say that f is not continuous at x equal to 1. And now we look to the point B, we look to the point x equal to 2. At the point x equal to 2, we can see from the graph that f2 is equal to 2. That means f defined at x equal to 2. And the number 2, limit of fx when x equals to 2 from left is equal to 1, and the limit of fx when x equals to 2 from right is equal to 1. From left is equal to 1, and from right is equal to 1. So, since limit of fx when x equals to 2 from left is equal to the limit of fx when x approaches to 2 from right. So we can say that limit of fx when x approaches to 2 is equal to 1. That means the limit exists at x equal to 2. And the number 3, since limit of fx when x approaches to 2 is not equal to the f2 or the value of fx when x equal to 2. So we can say that f is not continuous at x equal to 2. And the last one, we look to at the point C, at the point x equal to 4. So at x equal to 4, the number 1, f4 is equal to 1. That means f defined at x equal to 1. Sorry, f defined at x equal to 4. And the number 2, limit of fx when x approaches to 4 from left is equal to 1. And for our conclusion, since limit of fx when x approaches to 4 from left is equal to f4 is equal to 1, so we can say that fx is continuous from left at x equal to 4. Now we continue with the example 5. Given that fx is equal to ax plus b for x less or equal to 1, and fx is equal to x squared minus 1 for x is greater than 1. If fx is continuous for all value of x, find the value of the constant a. If we look to the given function, the critical point to this function is only at x equal to 1. So fx will be continuous on the entire real line if and only if limit of fx when x approaches to 1 from left must be equal to the limit of fx when x approaches to 1 from right, and must be equal to the fx when x equal to 1. So to solve this problem, we can choose any two of these three equations. So if you look to the limit of fx when x approaches to 1 from left must be equal to the limit of fx when x approaches to 1 from right. So the limit of fx when x approaches to 1 from left, so we must use the function of ax plus 5. So limit of ax plus 5 when x approaches to 1 from left must be equal to the limit of the limit of x squared minus 1 when x approaches to 1 from right. So by substitute x equal to 1, we have a times 1 plus 5 must be equal to 1 squared minus 1. So a times 1 is equal to a plus 5 is equal to 1 squared is equal to 1 minus 1. So a plus 5 is equal to 0. That means a is equal to negative 5.